Hey everyone, my name is Chung. I'm an engineer at Huawei Canada, and my talk's going to be about Gnocchi and how we handle time series data. So just as a little background about Gnocchi, Gnocchi is not a replacement Ceilometer. It's kind of addresses the storage performance issues, specifically around metering encountered in Ceilometer for the use cases such as monitoring, stats analysis, and other time-sensitive functions. So this is just a quick architecture of Ceilometer. Basically what it's designed to do is store time series measurements and their resource metadata associated with it. Specifically for my use case, what I needed was to collect usage information for hundreds of thousands of metrics across tens of thousands of resources for a couple of months to be used in capacity planning and scheduling. And also just take that data and throw it into machine learning algorithms as well. And the data that we're handling is received in batches periodically. It's not a constant stream of data. So to get started with our intro to Gnocchi, what we did was we created a baseline with what existed. The hardware we used was 3 physical hosts and a 1 gigabit network, so pretty decent machines and average network. And we started off with Gnocchi version 2, and I used Postgres for our indexing, Redis for our coordination, and Ceph for our metric storage. So for the test methodology, what I did was I posted 20,000 metrics across 1,000 resources with 60 points per metric, and I had a policy set up to roll up to a minute granularity, hour, and daily with 8 different aggregates each. And our first go, what I found was that in the first batch, it actually performed relatively well, but in every other subsequent batch, it dropped heavily in performance, and I wasn't really sure why. Because when we tried with other backends, such as the NFS backend, that same drop in performance didn't actually happen. So what I decided to do was actually learn how to use Ceph beyond normal Ceph deploy that you typically do to deploy Ceph. I started by doing what everyone does. I gave it more power. I added another node for Ceph. I added more OSDs, more placement groups, some SSDs for the journals. And the results were I got 65% better post rate, 27% better aggregation rate, and the same drop in performance, regardless if I had more OSDs or SSDs. And the chart shows right now is just the amount of metrics processed every 5 seconds. So I decided to go back and actually try to learn Ceph. So I played around with configurations, and the original configuration that I used is on the left, and then on the right is what we ended up with. The biggest boost in stability came from adding options to configure the file store queue size. The 50K values there are kind of arbitrary. They just kind of work for my scenario, and I didn't really look that much into it. And so this is just a graph of the changes in performance based on the configurations we chose. So as we increased the amount of threads we use in Ceph, the performance got better, and eventually the bottom line is what we ended up with, and you can compare it to our NFS solution, which is quite a bit better. So after we stabilized the Ceph performance, we started to look at how to improve Gnocchi itself. And as a baseline, we were computing about 29 aggregates per worker per second, which isn't really that bad, but we wanted to do a bit better than that. So we looked at minimizing the I/O we had in Ceph. Originally, we noticed that there was a lot of read and writes to Ceph. So what we looked at, the existing workflow in Ceph or Gnocchi was to read in the entire time series, update a specific point, and then write back the entire time series. And that was a lot of overhead. So in Ceph, what we realized is that we can just write to a certain offset and update one single point instead of having to kind of handle the entire time series itself. To do that, we had to change the storage format. Originally, we had a JSON, a serialized object as our storage format, and we changed that to a struct-based binary serialized format and compressed it. So we not only got better serialization time, but we got better object density. In addition to that, we started asking questions about the code itself. We started profiling the code. Like we knew certain parts of the code we just didn't really need. And there was other parts of the code where we weren't sure why it was being called that much, or in other parts where it took way longer than it should have. And then the ultimate goal was to increase the block size of the yellow, which is the I/O time, so to change it from being CPU bound to I/O bound. So for our results, after all the changes we made in the past few months, this is a graph showing the measures per second we can post. We can post up to almost 1 million measures per second with big batch sizes, which is about a 50% gain in performance. It roughly translates to about 300 to 1,300 posts per second with 32 API workers. The read performance was pretty much the same. Nothing really changed there. We basically we can pull in about 80,000 points in about 2 seconds, depending on, assuming the aggregates are already computed. To actually compute the aggregates, I tested that as well. To compute about 12,000 points, new points into aggregates, into 24 aggregates, it took about 4.2 seconds roughly, which is about 50% better overall, depending on the amount of new measures being pushed in. From this usage point of view, originally it was 16 bytes per point based on the JSON object we had. Now it's about 6.2 based on my test case, but it's really heavily dependent on your series length and when that compression algorithm kicks in. For my use case specifically, what we managed to do was we managed to get consistent performance between batches, where previously it kind of degraded over time, depending or as the series got bigger and bigger. So we got about 30 to 60% better performance rate there. And the biggest performance gains are when the series gets longer. And one of the good things about using Ceph driver is that we use a lot less I/O now. We have about 30 to 40% less I/O. Those numbers are based off the Ceph log, so they may be off a bit. So now, from before where we got 29 aggregates per worker per second, now we're up to about 53, and we can probably make more improvements to that as well. In addition to that, I started looking at playing around with different options and figuring out how we can improve just deployment scenarios and how to deploy it properly. I found out that by adding, for every granularity you add, if you add like hourly granularity or a daily granularity or even more, there's about a 15 to 25% overhead to compute additional granularities. And also just to compute percentile aggregations such as 95th percentile and 90th percentile aggregations, that actually takes the most amount of time. Also, because of our changes, now our process is more I/O bound, which is actually good for threading in Python. So now we can actually deploy about 25% less workers with threading enabled, and that performs exactly the same as having that full 100% that we had before. So this is just the HTOP of what our system looked like. The metric D agents that are working in the background are very CPU intensive still. So is Ceph OSDs, and so you should probably be aware of that when deploying both of them in a system. And some other stuff that we did this cycle, we added some functionality to compute aggregates of aggregates, so you can get the means of maxes, maxes of means, and other variations. We added support for dynamic resources, so you can create your own custom resources, add in your own metadata to that. And now you can aggregate on demand, so instead of having a lot of background workers aggregating your data points, you can actually query and say aggregate all the new unaggregated measures on query time. We also added support for Grafana 3, so now you can make pretty graphs and kind of visualize your entire system based on your requirements. And for future work, what we're looking at is just making the system a bit more user-friendly by adding like rolling upgrades, so the ability to do some fair scheduling of the unprocessed measures that we have, and to compute aggregates based on different granularities. So getting aggregates, your annual aggregates from your daily or hourly aggregates. So that's my presentation on Gnocchi. Thanks, guys.